In this last video for section 3.5, we're going to talk about the logistic growth model. So the point of this is that any kind of population can't just continue to grow indefinitely, right? So if we think about what an exponential looks like, it just increases forever. And so there is no thing in reality that can do that. And so somehow we have to limit the size of the population. To do that, or at least to model that situation, we use the logistic model, which is given here. A, B, C are constants. B and C both have to be positive. And if we would like to see what a graph of this sort of thing would look like, we can see that here on the right. So initially, the thing follows a very exponential curve, but at some point it has to kind of change its pace and start to decrease in the rate of growth. And eventually, it's going to reach an asymptote or try to reach an asymptote. It can't go past that point. So let's look at an example. Right here we have the logistic growth function that describes the number of people who have become ill with influenza T weeks after its initial outbreak in a particular community. How many people become ill with the flu when the epidemic began? So if we're asking when it began, that should be when T is 0. Okay, so let's plug in for A, T equals 0. So f of 0 is 117,000 over 1 plus 5500e to the negative 0. So negative 0 is the same thing as 0. And so e to the 0 is just 1. So we now have 117,000 divided by 1 plus 5,500, or 117,000 and divided by 5,501. So let's see what that gives us. So I'll do the calculation here. And if you're following along, go ahead and try it yourself. I get 21.27. Now it says how many people become ill with the flu when it began? 22.27. Again, this can go either way. Personally, I would go to 22 because there's a portion of another person. If we use our normal rounding rules, we would say 21. Second part of the question says, how many people were ill by the end of the 4th week? So we have to make sure that we're talking about T, and T is in weeks. So that means 4th, or T is equal to 4. So for part B, we're just plugging in T equal 4. So f of 4 looks like this. And once again, we could just go ahead and plug that into the calculator. Again, if you would like, follow along. If not, you can just skip ahead to get to the answer. Alrighty, looks like after T equals 4, we have 1,150 approximately. So that's after 4 weeks. All right, so the last part of the question says, what is the limiting size of the population that becomes ill? Which is where we're looking for the horizontal asymptote. So for this type of problem, right, basically we're saying as T goes on for a really, really, really long time. So we could just plug in a really large value of T and see what we get. So let's try that. Let's say F, and I don't know, let's just try 10,000. Let's see if that's sufficient. And so we have 117,000, 1 plus 5,500 e to the negative T, so negative 10,000. So I'm going to take the 117,000 divided by 1 plus 55,000 e to the negative 10,000. And the calculator spits back this. Doesn't give me an approximation. It just says that. In this example, we're doing another logistic growth model. And this time, f of x is in billions, and x is our years. We're not using t any longer. So the first thing they ask us is, what is the initial population? Well, that would be when x is 0, right? So x equals 1974, or sorry, the year 1974 is when x equals 0. So let's plug that in. So we have f of 0 equals 12.57 divided by 1 plus 4.11 e to the negative 0.026 times 0. And e to something times 0 is e to the 0, and e to the 0 is 1. So we just get 12.57 divided by 1 plus 4.11. And that is approximately 2.46. And keep in mind that's in billions, right? Second part of the problem says, what is the population in the year 1990? So we would need to know, what is x for that? Well, x is the number given minus the initial year, which was 1974. And so 1990 minus 1974 is just 16. So we're plugging in x equals 16 now, and then just calculating that value. So nothing too special here. The first one even nicer than the one we're doing now, because we just plugged in 0. So let's plug this in, 12.57 divided by the quantity 1 plus 4.11 times e to the negative 0.026 times 16. And so it looks like I get 3 point, and if we're going to 2 decimal places, 39 for that one. The last part says, in what year will the world population be 8 billion? So we're looking for f of x to equal 8. So this is a new challenge for us. We're saying, let this thing equal 8 and solve for t. Okay. Now, I'm going to let you guys in on a little trick here, just because you're going to do this a lot, and I don't want to have for you to keep doing it over and over and over again. If I have a number, a single number, equal to a fraction, okay, then I can simply move the denominator of the fraction to this side of the equation and then switch it with the constant that's on that side. Now you can sit here and you can do the manipulation and you can prove it to yourself, but this will work every single time and it'll save you time. So basically I'm just switching their places. Still got to get t by itself. So now I need to subtract 1 from both sides. So now I'm at 4.11 e equals 12.57 over 8 minus 1. Still got to get e by itself, so I'm going to divide both sides by 4.11. And I'm not doing an approximation just yet, because I want to keep this as close to exact as possible. So now I'm here. We know that to get rid of the e, I got to take the log of the other side, or both sides really, and so I get this. And the last step is to divide by negative 0.026. And so t is equal to 1 over negative 0.026 times the natural log of 12.57 over 8 minus 1 all over 4.11. And bear with me here while I go ahead and calculate that. So 12.57 divided by 8, subtract 1, then divide by 4.11. Then I need the natural log of that number. And finally, I'm going to divide by negative 0.026. And it looks like t comes out to, it's 75.898. Let's just go ahead and make that 76. And again, t was in years. So that's 76 years past 1974. So if I do 1974 plus 76, I get the year 2050. Because it did in fact say in what year. It didn't say how many years from now. So 2050 is the solution to that one.